So here we're given parametric equations where we're given x in terms of t and y in terms of t, and we're asked to find the gradient dy by dx. So whenever we have parametric equations, dy by dx will be the ratio of dy by dt divided by dx by dt. So what we now need to find is dy by dt and dx by dt. We can do that separately. So for x, it looks like it's straightforward. So dx by dt, the derivative of a sine is cosine, so it's half times cosine 4t squared. But because we have 4t squared rather than t, using the chain rule, we need to multiply by the derivative of 4t squared, of 2t squared, and that gives you 4t. So dx by dt is equal to, and if you multiply the 4t times half, you get 2t cosine 2t squared. So that's my dx by dt, and I can do the same for dy by dt. So let's do that. So my derivative dy by dt will be, and it looks like we have a product here. So the product rule, I'll just remind you, is u dash v plus u v dash. So if that's my u and that's my v, then it's going to be u dash 2 e to the 2t times cosine t squared plus the derivative of, so you keep the exponential, the derivative of cosine is negative sine, so I'll write it as sine t squared, and the negative, I'll just change that to a minus sign. But again, because this is not t, it's t squared, using the chain rule, we need to multiply by the derivative of t squared, which is 2t. So that's my dy by dt. And now I can use this relationship to find dy by dx. So dy by dx is the ratio of dy by dt that we just found divided by dx by dt. So that's my dy by dt. And in the denominator, I'll just copy my dx by dt. And that is the expression for dy by dx. Okay, so that's part A. That looks like all they want for part A. Find an expression for dy by dx. They haven't given us a specific point, so we just leave it like that. The question then goes on to say, find the equation of the normal at the point t equals 0. So to find the equation of the normal, we're going to need the gradient of the normal. And the gradient of the normal is the negative reciprocal of dy by dx at the point where t equals 0. So it's the negative reciprocal of that. So it's essentially the same fraction, but upside down with a negative sign. So I'll put my negative sign there, and then we'll just put the denominator in the numerator and the numerator in the denominator. And now I need to substitute t equals 0. So I'm going to have a 0 here. That can't be right. I think we missed something. Yes, there was this t here that I missed. So when differentiating dx by dt, I should have added the derivative of t, which was 1. So that goes there in the denominator and therefore up here in the numerator. So again, I'm substituting t equals 0, so that's a 0, 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 that's a 0. So cosine 0 is 1, and e to the power 2t, or e to the power 0 is 1, so that's 1, and that's a 1, and that's a 1, but this is 0. So we can simplify this as negative 1 over 2. So it's minus 1 over 2. So that's the gradient of my normal. Now, to find the equation of the normal, you need more than that. You need y1 and x1. So the equation of a straight line is y minus y1 equals m x minus x1. And the only thing we now know is m. So we still need to find x1 and y1. And if we look to the question, they don't really help us. They don't give us x1 and y1. But what we do know is x in terms of t, and we know t is 0. So I can find x1 by substituting t equals 0 here. So if I substitute t is 0, I get x1 equals 0. So that's the value I can put into there. And I'll do the same for y. Oops. Okay, so that's finally working. So I can simply put in 0 here and here. So e to the 0 is 1 times 1 is 1, and that I can put into there. So now our equation's looking much better. We have y minus 1 equals negative 1 over 2 brackets x minus 0. And if we multiply both sides by 2, we have 2y minus 2 equals negative x. Or we can say x plus 2y minus 2 equals 0. And that would be your final answer. That's the equation of the tangent, or the normal, at the point t equals 0. The question goes on to say, find the angle from the horizontal at which the firework is traveling. So at the moment when the firework is launched, it's following some path, and we know the equation for the path, but they're asking for the angle with the horizontal. So if we look at the initial point, t equals 0, presumably that's the moment that the firework is launched, then they're asking for this angle here, okay? And that angle we can find by finding the inverse tangent of delta y divided by delta x. So we can say theta equals the inverse tangent of delta y by delta x. Because the tangent of the angle, by definition, is the opposite divided by the adjacent side. So the opposite side is delta y, and the adjacent side is delta x. But delta y over delta x is really just dy by dx at that point t equals 0. So theta equals the inverse tan of dy by dx, or the gradient of the tangent. So we found dy by dx up here. Well, we didn't find it, but we found the gradient of the normal. So if we were to have found it, if we had calculated it at the point where t equals 0, we would have got 2, because this and this need to be negative reciprocals, remember? So the gradient of the tangent was 2. So if we go back, we can say theta equals the inverse tan of 2, which is 63.4 degrees. Make sure your calculator is in degrees when you're doing this. You can do it in radians, certainly, but make sure if you do that, you mention that the answer is actually in radians. But I'm guessing they would want this in degrees. So that's how to find the angle from horizontal. It's always the inverse tan of dy by dx, the gradient.